protocol. So this is inter-domain routing. This is the common protocol used for inter-domain routing, which means routing between autonomous systems. So we had earlier looked at intra-domain routing, which is routing within an autonomous system. So between autonomous systems. So what have we looked at till now? First of all, we started with switching at layer 2. So we said there may be an Ethernet switch here and another, let's say, various LANs. Okay, so this could be a layer 2 switch. And there could be an, let's say, a layer 3 router over here which connects this whole network to the internet. So let's say this is one autonomous system. And this autonomous system, let's say, is connected to another one. Right, so there are lots of, let's say, routers and whatnot, and then we are connected to various other autonomous systems. I'm just drawing the edge routers which are connected to other autonomous systems. And let's just call this autonomous system, let's just call it A. Right, this is, let's say, autonomous system W. So actually in practice you don't give letter names, but you would give a number. So it might look like AS100 or AS200 and so on. Right? So they are given these autonomous system numbers. Okay, let's just call this ASB. Let's say this is autonomous system C. And I mean, there are lots of these various autonomous systems. Okay, let's say there is an autonomous system Y here. And let's say there is somebody else here, whatever, autonomous system Z. So of course the internet is much more complex than this. There are lots of autonomous systems, but this is what it would look like. So I've shown the layer 2 network here. At this level here I've just shown you a few of the layer 3 routers, and for these of course I haven't shown you any internal details. Okay, so we are just looking at it at the autonomous system level. Okay, so the ASs together form a network, as you can see over here. Okay. And border gateway protocol BGP is used to communicate routing information between these different autonomous systems. Okay. So this network at the edge over here could be a customer. So this, let's say IIT is a customer, for example, and it could have many different connections to the internet. Maybe one through Reliance, one through National Knowledge Network or whatever, right? So So this sort of an autonomous system which is connected to multiple other autonomous system and it is paying them for service. This is called a multi-homed customer. So who's the customer and who's the provider? Well, it really depends on who's paying whom, right? So let's say this person wants internet service and he's paying these two people, these two autonomous systems. So I'm calling him a customer, right? And since he's connected to more than one, he's a multi-home customer. Okay, so let's say at the core of the internet, you may have, let's say, large autonomous systems which may be nationally connected, right? Let's say maybe in India, Geo may be very largely connected. In the US, you may have some other Sprint or something like that, right? Or AT&T connected throughout the country. And those autonomous systems may not be paying anybody else for internet service. Everybody else is paying them. And in that case, they are called tier 1 autonomous systems. So okay, so usually they have a wide network connectivity. Let's say across a country or even the entire globe. And usually these tier 1s do not take internet service from anybody else. They are not customers for anybody else. And this one also may be tier 1. Okay, so let's say that both of these are tier 1. And let's say this autonomous system is taking internet service. Let's say this one is a local network. It's not very largely connected, let's say throughout India or the US or wherever. Right, so what it does is it takes internet service from this tier 1 autonomous system. So it might be a tier 2 autonomous system. Okay, so it takes internet service from, let's say, a tier 1 ISP. Right, and then maybe you could have tier 3 autonomous systems, tier 4 and so on, right? So these are just terms that people use to describe them. It depends on whom you're taking internet service from, right? So if you're taking internet service from somebody, then you're probably one tier lower than that provider. And at the edge, you may have somebody who's just taking internet service from somebody else, right? And he's not providing service to anybody else, and those sort of people we would call customers. Okay, so this customer network is not providing internet service to anybody else. There is no, you can say, no tier below this one. So this is roughly how you would call these autonomous systems, how you would divide them into categories. Now sometimes it may be that this tier 1 autonomous system is not very widely connected to everybody. So you can see that it has a connection to A and to Y, but it's not so well connected to this autonomous system X. Right, and this autonomous system X may be connected to autonomous system B. It's getting internet service from this one. So what you may have in practice is you may have these two connected to each other, what is called a peering link. So these are both tier 1 ISPs. So they are called peers. They are sort of equals, and they are not paying each other, but they still, out of goodwill, they have this peering link between them. So for autonomous system, this is autonomous system C. C wants to send packets to X. How is it going to do that? It would normally send it through B. Okay, and it reaches X. It would go this way, and that's where this peering link would be useful. Okay. So both don't pay each other, but each of them is allowed to send some amount of data to each other, just because that's a more convenient way of sending traffic, let's say, to their own customers. So because these peering links are not paid for, it's sort of, you're not paying each other for this service. Usually these peering links, the bandwidth won't be too high. Okay, so it's enough to sort of, for you to send data to somebody else, but you don't want to have a huge amount of capacity over here, just because somebody might misuse it. So suppose, for example, this link was suppose this was, let's say, only 1 Gbps, and this was, let's say, 10 Gbps, this particular peering link. Then autonomous system C, suppose somebody within autonomous system C wants to send data to A. Autonomous system C might cheat in some sense. He might just dump all the traffic onto B and say that you deliver it to A. I will keep this for some other purpose. So if you can give other people your work, that is sort of the way to do it easily, right? So if they are peers and they're not paying each other, then why not do that? So if C has data to send to A, I dump everything, and wherever I am getting money to be paid, I use that more effectively. Okay, I get money from people. Maybe I get some money for this traffic to somebody. Somehow I'm getting this traffic meant for A, but I don't send it on my links. I give the traffic to B, who sends it to A. So because of that, these peering links usually have not such a high bandwidth compared to other links. Okay, so this is usually under provision. Because both don't get paid. For delivering the traffic on that link. Okay, so how is BGP going to work? So this is what the topology might look like. You have different people, connected to different autonomous systems. There are some peering links and so on, and there are some agreements reached between them. That let's say autonomous system A will tell W that this particular link I am guaranteeing is, let's say, 1 gigabit per second. You can send it to me at 1 gigabit per second, and I'm guaranteeing that it will always be up, let's say 99% of the time over a period of 1 month. And also he will give some other guarantee. He might say that your packets will stay in my network for only 35 milliseconds or something like that. And that is called a service level agreement. So the service level agreement is some sort of a quality of service guarantee. It's saying what is the throughput you can expect on this link for how much time, and also what is the latency across my network. So A cannot guarantee anything about end-to-end latency, right, or end-to-end throughput, because it doesn't have control over the full path. It just has control over the paths within its own network, right? So there could be other routers here and so on. Okay, so they have SLAs between them for some sort of service, and then what happens? How do packets find their way from one end of the network to the other? So we've seen how packets can go from, let's say, this router to this one. There is an intra-domain routing protocol. So the network operator can put any sort of link cost, and the intra-domain routing protocol will find the shortest paths, right? Or they could do things like load balancing, which we've discussed in some of the live sessions. So, but how do you know how to route a packet to somebody outside your network? So that's where BGP comes in. So let's say that W has a particular prefix allotted to it. So let's say all these machines correspond to a particular prefix. Let's just say that is x.y.z.w/n. This is the IP prefix here. So it could be a /24/16, whatever. Now this autonomous system wants everybody in the internet to know about it, right? So somebody else, let's say in Z, might want to send a packet to a machine here, and that packet has to find its way all across. So what BGP is going to do is it's going to announce this information to everybody in the network, so that there is an autonomous system path. So it's a path at the AS level. So if you abstract this network out where each of these autonomous systems is one node in the graph, BGP is going to help you find a path across that particular graph at the AS level. Okay, so suppose this packet from Z is supposed to reach here. Suppose it's choosing this path X, B, A and W. Okay, so how is it going to work? First of all, the packet, let's say from somewhere here, has to find its way to this exit router, right? So it will have to find its way here, and this will forward the packet to what is called the next hop. In the next hop is the router in the next autonomous system. Okay, and that's the best that autonomous system Z can do. He's figured out there is some path at the AS level, and he knows that X is the next hop at the AS level. Okay, so he delivers the packet over there. Then it's again the job of the intra-domain routing protocol to send the packet across to the border router, which will forward the packet to the corresponding router in the next autonomous system, right? So this continues. The intra-domain routing protocol has to figure out how to get it all the way to the edge and then into the next autonomous system, and that keeps happening till it reaches the appropriate destination autonomous system. And then here, of course, the routing tables have to be set appropriately, the subnet masks and so on at various routers. And layer 2, of course, will finally kick in. I mean, everywhere actually there is layer 2 also working, though we are sort of skimming over that. And finally the packet reaches the destination. So really what BGP has to tell us is, how do we find this autonomous system path? Right? And what if there are multiple paths? Maybe there is this path or there is this path which reaches here. Okay, we have to choose some particular path somehow, and we have to ensure that there are no routing loops. Okay, so all of that has to be done, and the question is, what information should they share? Okay, so let's say that there is this particular W which we are focusing on, which has this particular IP prefix. So what will happen is that this router, let's say this is a BGP router, and any router which runs BGP is called a Bgp speaker. Okay, so let's just write it here. It's a Bgp speaker, which means that it speaks the BGP language. Okay, so both of these, let's say, are Bgp speakers. So first, these two are going to talk with a protocol called Ebgp. So this is external BGP, where they are going to announce information. So for example, this router, let's just call this R1 and let's say this is R2. So R1 can tell R2, it will say that I have this prefix x.y.z.w/n, okay, this particular prefix, and this is the AS path. So I am the only autonomous system. This prefix belongs to me. This is called the AS path. Okay, and besides this, there are some attributes. We look at them. So this is an advertisement. So this is an example of a Bgp advertisement. Okay, so this is R1 to R2. And let's say that this is R3 and this is R4. So here too there is Ebgp running between them. Okay, there is a Ebgp protocol. Okay, and using this Ebgp protocol, so this is R3 is going to tell R4. Okay, so first of all, how does R3 learn about this? So we are going to advertise the same thing. So R2 and R3 will have to communicate with each other because R2 has learnt about this particular Bgp prefix. So they communicate using a protocol called Ibgp, Interior Border Gateway Protocol. So both of these belong to the same autonomous system. So they have some internal communication which is done over this protocol. Okay, and so what is R3 going to tell R4? It's going to say x.y.z.w.n/n. So it's saying that I am aware of this prefix, and my path is to that prefix is AW. This is the AS level path. Plus there will be some attributes. So attributes are some extra information, and we'll see some of the attributes that can be handed out. Okay, and similarly it continues. This could be R5 telling R6. Also over Ebgp. So this is Ebgp. Okay, it will say the same thing, but the path gets longer, and essentially you put the autonomous system numbers here and then the attributes. Okay, so as you're going further and further away from autonomous system W, the AS path is getting larger. So what does this mean? So really, when R5 is telling R6 about this, he is saying that the autonomous system level path from me to reach this particular prefix is BAW, and it also means that I am guaranteeing, so R5 is guaranteeing that if you send me an IP packet whose destination IP address matches with this prefix, then I will definitely send it along this path to the destination. Okay, so this is saying if R6 gives R5 an IP packet with the destination IP matching this prefix, then it will definitely route it along AS path BAW. Okay, so this is a guarantee. So you can't send out any sort of advertisement you want. Okay, that would create chaos in the internet. So this is if you make such an announcement, you're giving a solemn guarantee that if you get a packet with that particular destination address, you will route it along this path till it reaches the destination. Okay, and it will finally reach it. So of course B is only guaranteeing that it's sending it to A, but A has also given a similar guarantee that he will give it to W and so on. Right? Okay, so once these advertisements have been made, R6 sort of knows that if he sends a packet here, it will finally go along this path till it reaches W. Okay, so the question is, what information are we going to send by Ebgp? Okay, so here of course this autonomous system has to tell people about his IP prefix, otherwise other people will not be able to send packets to his machines. It doesn't make sense. So of course he will announce this to his own ISP. Okay. Now we talked about this peering link, and we said that you don't set the peering link capacity to be very high because C might want to cheat. He may want to send a lot of packets to B, so that B does the job of sending it to the destinations. Okay. So it may be possible that B doesn't even want to tell C about his path to A. Okay. So if he tells C about his path to A, then C might try to cheat by sending a lot of packets this way, so that B delivers the packets here. And he will use this for whatever purpose he wants. So whatever gives him more, maximizes his profit. Okay, if he congests his own link with those packets, then he can send less data. Okay. Anyway, so B may want to keep certain information secret. And in that case, BGP allows it. So B may keep certain paths secret. So B does not have to tell he does not have to tell C that there is a path BA, or that there is a path BAW. Okay, so he's not compelled to give this information. And why is that? Well, because this is not a government controlled network. These are all private companies. So there is a lot of money to be made here, right? After all, it's the internet. And different companies which are competing with each other may want to keep certain information secret from each other. Right? So BGP doesn't compel anybody to say whom he is connected to. Right? So you can keep, B and C may completely keep some of their connections quiet. I mean, they won't tell each other about those connections. Right? So also, for example, suppose Z is connected to both Y and X, right? But he may not want to tell. So he's a customer. Let's say it's an IIT or somebody like that. So he may not want to tell X that he is connected to Y, and he may not want to tell Y that he is connected to X, because otherwise X could send packets destined for Y through Z. Okay, if he tells them about both these connections, they may use him as an internet service provider, okay, so that they can connect to each other. Whereas he is paying both of them, he's a small network and he doesn't want to get his network flooded with these packets from X to Y, right? So Z2 doesn't have to tell the other people about whom he is connected to. He will just tell Y what his prefixes are, and he will tell X what his own prefixes are, right? So customers too may want to keep some of their connections hidden from each other. So BGP doesn't compel anyone to tell all the information about their connections to other autonomous systems. They can choose to keep it secret, right? But of course you hope that your internet service provider is going to tell other people, at least one other network, about your prefix, because after all, if A doesn't tell B and C about this prefix, then nobody is going to be able to connect to W. In summary, each autonomous system's routers which are connected to other autonomous systems, like for example R2 and R3 in this autonomous system A, they are going to learn about various Bgp advertisements from neighboring autonomous systems through the Ebgp protocol. And they have to exchange that information with other routers in the network, because after all, suppose a packet comes in, let's say, to any particular router, right? And that particular packet has destination address for this particular autonomous system W. The packet should eventually reach this router and go here, right? So these advertisements first of all have to be exchanged with other Bgp speakers which are connected to other autonomous systems, but also somehow that information has to be disseminated within the autonomous system, so that every router sort of has some information about what is the next hop, what is the next router, in order to send that packet to, so that it eventually reaches the destination. Okay, so it's a little bit tricky to get all of this to work, because first of all there could be multiple paths to a particular IP prefix. You know, maybe this x.y.z.w may come to this autonomous system Y. Maybe it will learn about this route, so it will learn about BAW, but it may also learn about route CAW. Okay. And in that case, it may have to make a choice which particular one to use. Or there may be certain instances where some packets go this way and some other packets go this way, right? So given these multiple routes to the same prefix, you have to make a choice. Okay. Also, there are more complicated situations where you may have, for example, this prefix getting aggregated into, using supernetting, it may get aggregated into a larger, I should say a shorter prefix where this n is a smaller number, right? In that case, you may actually have multiple prefixes which match the destination IP address, right? So getting all of this to work, and how do you sort of relate these, what is learned over here with what is learned elsewhere and so on, how do they disseminate the information? And so we'll talk a little bit about that now. So how exactly is all of this done? So Ebgp is a protocol between Bgp speakers in different autonomous systems. And what I mean is here neighboring autonomous systems, right? So usually these two routers are directly connected to each other. this is in one autonomous system and this is in another one. And just as a side note, they use a TCP port number 179. Okay, so usually we haven't yet talked about TCP ports and so on, but though you've used ports in one of your lab sessions, right? You had to choose a particular port number. So for certain applications you have standard port numbers. Actually this is 179. Okay, so port number 80 for example is used for HTTP, right? And email might have another standard port, so that if you want to use a particular application, you want to connect to a server, let's say running a particular application, you know which port to connect to. Anyway, so BGP uses this particular port, right? Then you have Ibgp, which is the protocol between Bgp speakers within the same autonomous system. So within the same autonomous system. So let's say this is the autonomous system and this is router R1, right? And so R1 might learn about some advertisement through Ebgp, and it has set up TCP sessions with all these other ones. So the most basic method is that all of them, you have pairwise TCP connections. So they share whatever information they have learned over Ibgp. So there are these sessions between them. I'm not showing you the intermediate routers, but essentially these different border routers which are learning about these advertisements, they have TCP connections between them. Okay, so there could also be, let's say, another router over here which is a Bgp speaker. Maybe it's not connected to some external router. Okay, it's possible, but it is running the Bgp protocol, in which case you would have a connection to that particular router. Okay, so I am showing all the Bgp speakers. So any particular router which is running the Bgp protocol, I am calling a Bgp speaker. Right, so if you have n of these routers, then you have order of n square connections. Okay, so each of them is learning about different advertisements, and then they share that information with each other over here, okay, through this Ibgp. Now also within the network is the intra-domain routing protocol, which is called IGP, Interior Gateway Protocol. So if you read up any of the literature on BGP, you will see that you will see some term like this, right? IGP, but this is just the intra-domain routing protocol. So usually it will use link state routing or distance vector. Okay. And now suppose you have learnt about different BGP routes, you might have to choose a particular route. You may have multiple routes to the same prefix, and in that case you would have to decide. Okay, so what are the steps of sharing information first? So let's say steps to decide BGP paths to use. So first of all, Ebgp speakers learn AS level paths from neighboring AS. Okay, and then they share this information using Ibgp. So Ebgp nodes share this learned information via Ibgp with their other Bgp speakers. In their own autonomous system. So that's not enough. So it's initially, of course, each of them has learned some information. So the whole network doesn't have that information. So at least they share it with other routers which are speaking Bgp. Okay, so still not everybody in the network has all the information, because there could be lots of routers which are not running Bgp. That too is possible. Okay, so let's say there is a non-Bgp speaker here. I mean, there is a non-Bgp node. So it may be only running the interior gateway protocol, but it doesn't run this Bgp protocol. Okay, so at least all the Bgp nodes after this step have learned all the information. Okay, so now these Bgp speakers are going to decide on paths. So they select routes to various IP prefixes. Okay, and we'll see how exactly they do that. Okay, so at this point, not all routers know about the paths, but let's say that at least Bgp speakers have somehow together decided on how to reach particular prefixes. Okay, so we have to somehow, to get the whole thing working, we have to sort of share that information somehow with these routers who do not know Bgp, who don't speak Bgp. So we have to insert these chosen routes into the IGP protocol. Okay. Since all routers in the network have to be able to forward all packets, right, for any particular destination. Since all routers must be able to forward packets. To a particular any destination IP, right? So what I mean is, suppose this is a Bgp speaker, this one is a Bgp speaker, and let's say that they have decided that for a particular IP prefix, this is the exit router, this is the one going to send it to the next autonomous system. Okay, so we're focusing on one particular IP prefix, but inside this particular network, this could be a non-Bgp. You could have, let's say, non-Bgp routers here. Okay, and so the packet has to go over here, but I mean when you will send it to this router, right? There's no direct connection between these two. So you send the packet here. This router has to be able to forward that packet based on the destination address, right? So it's not enough if just these two are aware that this is the exit router sort of to send it to the next autonomous system. These two have to know how to forward the particular packet, okay? So this particular step is going to take care of that. So if these routers now get a packet, let's say for that particular IP prefix, let's say some particular IP prefix, and there is a match, they will know how to send it along the path so that it finally reaches this particular router. Okay. And once, let's say, this particular autonomous system, let's say, has decided to forward packets this way, it can make an announcement to other autonomous systems. So this, let's say, this is within one autonomous system. Okay, it has decided that it will forward packets this way to this particular prefix. Now it can announce it because after all, if you're not willing to forward a packet to that particular prefix, you shouldn't be making announcements, because when you make an announcement, you're giving that guarantee that you will forward the packet. Okay, so after this step, you can advertise a particular path. You can actually say, suppose this is going through B to A to W. Okay, you can make an advertisement, let's say to some other autonomous system, that I have this path all the way to this particular IP prefix. Let's say this is autonomous system, I forget what we have, autonomous system Y, let's say. Okay. So Ebgp speakers can advertise newly created routes to other autonomous systems. To neighboring autonomous systems. Okay, so these are the steps to be followed. So let's discuss a little bit about Bgp attributes. So these are helpful when you want to choose from among different routes to the same IP prefix. So the first one is called local preference. So suppose this is autonomous system 2, and let's say it is connected to autonomous system 1 and autonomous system 3. So these are the border routers, so they are connected through Ebgp. And let's say that there is a particular prefix 172.16.1/24. Okay, and we have from somewhere, and we've learnt about two paths. Okay, and both these autonomous systems are advertising routes to this particular prefix. Okay, so they are advertising this prefix 172.16.1/24, and they give the AS path. So they say AS3 and ... This is the path. And similarly, there is another advertisement here for the same prefix, AS1 and so on, the list of autonomous systems. Okay, and of course this advertisement can come with a set of its own attributes. Okay, but this local preference is an attribute which is created by the network administrator of this local AS. So administrator of AS2 adds the local preference itself So why does he do this? So he might actually say that I want to prefer one path over the other. I mean, you have to give the administrator the freedom to do that. So this is what gives him that freedom. So he might say that local preference for one path, let's say, is 50 and the other one is 100. And here the local preference. Okay, so this is added by the administrator of two. So the advertisement is coming from these neighboring autonomous systems, but this local pref is added here locally. Okay, so the network administrator might actually log into these routers, and he will actually hard code these, and he will say that, you know, all advertisements which are of this kind coming from here, they will have 100, and local preference for these is 50. Okay, so when this information is shared with other people, these local preferences will also go to other nodes. So let's say that there is a router here which is connected through Ibgp to these. So the local preference for these advertisements are sent along to this router. Okay, and they are added, let's say, by these routers themselves within this particular autonomous system. Okay. So higher local preference indicates a better choice. So higher local pref implies more preferable path. Okay. So we'll see how to put all these attributes together, but right now I'll just define them. The second is called multi-exit discriminator. MED. Now MED is actually given by the neighboring autonomous system. So suppose this is autonomous system 1 and this is autonomous system 2. So suppose there are multiple connections between this autonomous system, both of them, that too is allowed. And let's say that there is some path over here to 172, the same one. So there is an advertisement being sent over here for that particular prefix, and of course this will have an AS path. Now this particular autonomous could give an MED attribute. It doesn't have to, but it could give an MED value. And let's say it gives MED equal to 2000. And here this particular router is sending this one an advertisement. And a path. And the MED attribute. Let's say that it gives MED equal to 1000. So this path might be the same. Okay, it could be that there are different paths also that might end up being the case, but it could be that there is the same path being advertised from both these routers. But this autonomous system wants to say that I prefer if you send me data for this prefix on this link. So let's say this is R1, 2, this is R2, and this is R3, R4. So this means AS1 is saying, it's telling AS2, I prefer that you send me packets for this prefix 172.16.1/24 on the link R4 to R2. Okay, this is the lower MED. Okay, so if there are different exits, this MED is sort of discriminating between them. It's saying AS1 is telling AS2, if you send me a packet for this particular prefix on either of these, I'm going to deliver it. But I would prefer that you send it to me from R4 to R2. So why might it want to do that? Well, maybe let's say the interior gateway protocol, the intra-domain routing protocol, maybe the cost to this particular router, let's say R5, may be less. I'm using, let's say, link state routing or whatever. Maybe this is the cost, there's some cost here which is less than this one, which is why you're saying that I prefer that you send it to R2. Okay, just because the cost for me in some sense is actually less that, right? So you might just set your MED value equal to your IGP distance, let's say from R2 to R5, and this maybe the distance from R1 to R5 may be 2000. Okay, you set as the MED value. Okay, so local preference is set by the autonomous system which is receiving. After receiving the advertisement, it adds the local value depending on its preference. Okay, or it need not add a local preference to if it doesn't care. But MED is suggested by the person who is sending the route. Okay, the autonomous system sending the route to the neighbor. So a third attribute which we've already talked about is AS path. So AS path is just the list of AS numbers all the way to the destination with that IP prefix. Okay, so by destination I mean whoever originated with that IP prefix. Let's say whoever first advertised that IP prefix. So we have to take into account things like supernetting. Okay, so some autonomous system down the line might aggregate some particular addresses into a larger prefix and send that out, right? So that in that particular case, that autonomous system would be the last one in this particular advertisement. Okay, so just to make things more clear, so I said, for example, that there are several autonomous systems. Right, and let's say this autonomous system, I think we had something .128, right, and this went all the way to 135/24, and we combined that into something I think 128/21. We combined these all, right? So this may be autonomous system 1 onwards, and this may be whatever autonomous system, say this is autonomous system 8 and this is autonomous system 9, right? So this autonomous system is might advertise this particular prefix. Okay, let's just say 172.16.128. So okay, and somebody down the line here, let's say you have AS10, AS11. So So when this autonomous system advertises the prefix, it might advertise this supernetted prefix. It will give the AS path. It will say AS11, AS10, AS9. Okay, so although I mean the packet may be destined for AS1, right? That may be maybe AS1 actually contains a physical machine which has the destination IP address in question. But my point is that this AS path attribute which we send out, any particular AS sends out, it will have the entire path all the way up to this autonomous system which originated this particular prefix, okay, which first advertised. Okay, it will not have AS1 over here, even though actually the packet will be sent. So what's going to happen if at all this particular route is used? The packet will go along this particular path till it reaches here, and then AS9 will send it to AS1, whichever one has the whichever one has that destination IP address. Okay. So the next attribute is the next hop. So suppose there's this autonomous system, let's say AS1, AS2 and so on, AS3. So this is the last router within this autonomous system, and it is connected to, let's say, one autonomous system here. Okay, let's say we have a situation like this. And let's say that there is an IP prefix here, let's say 150.10/16. Okay, let's say this particular whole prefix has been allocated to this autonomous system, and let's say this has a particular IP address. Let's say this interface has IP address 150.10.1.1. And now let's say that there's been an advertisement over here about this prefix. This has been advertised from AS2 to AS1. Okay. So suppose packets have to be routed along this path. How are they going to do it? Because after all, eventually you're going to use the interior gateway protocol. Okay, and so somehow you have to know which is the next router, which is sort of the last router. Okay, so that's where this next hop attribute comes in. So the info that AS1 has about this advertisement is the following. So this information is shared with other routers using Ibgp. So it will have this prefix 150.10.16, and it knows that, let's say that this is the next autonomous system, but there is also a next hop attribute, and the next hop is the router here. Okay, so 150.10.1.1, and this is the next hop. So this is the IP address of let's say the first router in the next autonomous system. Okay, so essentially it's telling you which is the exit. Okay, so these routers, so let's say this particular link is also included in the IGP, the Interior Gateway Protocol. Let's say you put some cost or whatever, and you broadcast this IP address. So all these other nodes, even if they don't speak BGP, they know how to send a packet here just from the Interior Gateway Protocol. Okay. So this next hop information is useful here. So let's say that there is another prefix here, 160.10. Let's say this is also a /16 address. So the information at autonomous system 1 would look like this. Okay, so the route would get advertised this way. So there is AS2, AS3. This is the path. And the next hop again is 150.10.1.1. Okay, and of course there could be other attributes too. This particular autonomous system might give an MED attribute, which would also be there. But this autonomous system could also add its own local preference. Right? So this information is shared. They not only know the prefixes and the autonomous system level path, they also have the next hop and the other attributes. Okay, so this is a lot of information. So let's look at the rules to choose routes. So each BGP speaker uses the following rules to decide which particular route to use in case there are several advertisements for the same IP prefix. Okay, so each BGP speaker decides which AS route to use among many available for the same prefix. So first of all, remember that each BGP speaker is using this, so it's possible that the autonomous system doesn't use only a single route to a particular prefix. Okay, we'll see why that might happen. So each BGP speaker is going to use these rules to decide which particular AS level path to use. So first of all, use the one with the largest local preference. So in case the network administrator prefers one particular route, he just has to put the local preference highest, and then all BGP speakers are going to use that particular route. So in case this doesn't work, I mean this doesn't choose a unique path among all the ones available. Okay, so for example, suppose no local pref was set, or just the default value was used throughout, right? So this doesn't solve the problem, and then we go to the next one. Okay. So we choose a path with the shortest AS path. So this particular attribute Okay, let's say that there are two routes. One has 4 autonomous systems on the path, one has 3. You choose the one with 3 autonomous systems. Okay, provided that gives you a unique path. Now it may happen that you have 2 different paths, both have the same local preference and they have the same length of path in terms of autonomous systems. Okay, so I just write here, this should be number of ASs on the path. Then we go for third choice is through MED. So choose path with the lowest MED. So MED, I said, is given by the person who is advertising the path. And of course, if he's giving 2 different paths, he might tell you which one he prefers you to use. Okay, so normally you would only want to compare MEDs for the same autonomous system which is advertising it. Right, so let's go back here. Right, so I said that this one is 1000 whereas this one is 2000. Okay. And if suppose both these paths had the same local preference and both had the same AS length and so on, okay, then they would choose the path with the lowest MED, which in this case would be this one. Okay, but it's possible that somebody else also, some third autonomous system, might again give you a path to the same prefix and he might put an MED in there. Okay, so you can compare MEDs even across different autonomous systems, across different advertisements from different ASs. Though strictly speaking, MED from the same AS makes sense, because I mean he can put any number here. Really what matters is which one is more preferable to the other one. Right? This person might give MED 50, right? But does his 50 is it comparable to 2000 or 1000 here? You know, I mean, there may not be any relationship between the numbers that this autonomous system is giving, let's say this one, compared to what one is giving AS2. Okay, but you're allowed to use MED even across autonomous systems and choose the one with the lowest MED. Okay. Suppose this too doesn't give us a unique path, so maybe there are many which satisfy all of these. Then what you do is you choose a path learned over Ebgp over a path learned over Ibgp. So choose path learned over Ebgp over path learned by Ibgp. So what does this mean? So suppose I have a situation like this. Okay, so let's say that there is a particular prefix which has been advertised and there is an AS path. Let's say that the AS path and the MED and everything are, AS path lengths are the same. So there's one advertisement here and another one here. Okay, and MEDs and local preferences are the same. Now, so let's call this one R1. R1 is has learned this particular advertisement. Let's just call this advertisement 1 and this advertisement 2. He has learned this over Ebgp from his neighbor, but he has learned about this one over Ibgp. And since everything else was equal, AS path lengths and MED and local pref and so on, R1 will choose to send packets to this prefix over this route. So R1 sends, this is what he chooses to send to x dot y dot z dot w slash n. Okay. And what about this one? What about R2? So you can guess the answer. R2 has learned this over Ebgp and this one over Ibgp. He has learned about advertisement 1 from R1 and he has learned it over Ibgp. Okay. So R2 chooses to send it this way, packets this way. Let's say this one, to send packets to this prefix. Okay, so along with this there is a next hop. Okay, so I'll just to be clear what I mean by using an advertisement. So I mean that if R2 has a packet which needs to be sent to this particular prefix, he will send it to this router in this autonomous system which has sent him this advertisement, right? Whereas R1 is going to send it to the router which sent him the advertisement this way over Ebgp. So in this particular case, the autonomous system is not using a single route to this particular this particular prefix. This router is sending it one way and this one is sending it another. So what about, let's say, some router R3 over here? R3 has learnt about both advertisements over Ibgp. So even choice D doesn't solve the problem for R3. So what are we going to do then? So choose path which has the lowest IGP metric to the next hop. So choose path with lowest interior gateway protocol, that's the intra-domain routing protocol, to next hop. So what does that mean? So there is some next hop over here and there is some next hop over here, right? So we are assuming that these links are also advertised. Let's say that these links are part of the IGP protocol, right? So R1 can say that I'm connected to this next hop and this is the link weight, right? So it's advertised. So R3 looks at the distance and he sees, let's say that the distance from R3 to R2, okay, and he compares that to his distance. Maybe I should, instead of calling that, I just call this N1 and N2. So he's going to compare these distances based on the metrics, whatever the link weights are here, he finds the shortest path and whatever that distance is. So he compares these, and based on this, whichever one is smaller, he will choose that as the appropriate path. Okay, so suppose this is greater than this thing, this distance, and this, from this particular choice, R3 chooses, he chooses advertisement 1. Okay, so if at all he has a packet, he would send it to this particular next hop. Okay, and from there on, it would be the job of this autonomous system to send the packet appropriately. So that almost solves the problem. So of course this has a special name, it's called hot potato routing. So it's a little bit of a funny name. So why do we call it hot potato routing? So if somebody puts a hot potato in your hand, what do? Right? You would get rid of it as quickly as you can, because otherwise it burns your hand. So you give it to somebody else, right? Or throw it out or whatever, right? So this is the idea. R3 has got a packet and he wants to get rid of it as soon as possible. So he sends it to the nearest exit, whatever, let's say N1 is the nearest exit, and he just sends it that way and gets rid of it. Okay, the easiest way to get rid of it is his choice. Okay, so that's why they give it this name. So what if none of these end up with a single solution, right? Maybe the distances to N1 and N2 are the same, then what does R3 do? In that case, it uses the router ID. Okay, so use the router ID. Okay, and this is what I mean here is that we choose the lowest router ID among all Bgp speakers let's say who have sent these advertisements. Okay, so who are the ones who have sent these advertisements? R1 and R2. So I will look at the lower router ID among them. Okay, and what is the router ID? So we saw something at layer 2, we talked about bridge IDs. So here router ID is going to be the lowest or highest IP address on that particular router. So notice that each of these routers will have several different interfaces and each of them will have its own IP address. Okay, so we take the highest of those, and that is a convention. I believe Cisco does that, and that becomes the router ID, right? When they send these messages, they will send their router IDs also. So this is used as a final tiebreaker to choose any one of these two, right? So you might say, why do we need a separate IP address for each of these? That's a question which might come to mind, right? And it gives you the flexibility that you may have routers which are connected to different networks. Okay, so it's possible that you will have routers connected to different networks and so on, and the convention may require it to actually have an IP address belonging to a particular prefix for that particular network. Okay, so in general you would want to put a different IP address here, and you have the flexibility to do that, right? Okay, so we use these different rules to actually decide which particular route to use. Okay, and each Bgp speaker is going to do this. Okay, so we have to make sure that all of this is going to work properly, right? I mean, it seems a little bit weird that each person is making his own decision, and how does it all work together with the interior gateway protocol? Because there could be many routers which are not even Bgp speakers. So how does it all work out correctly? And that's what we look at in the next lecture.